In this video, we're going to take a look at a way to measure arc length and surface area of a function or of a plane described by a function. So let's start with arc length. Let's say that we have a function given to us, defined on an interval from a to b, and so we could think about this interval having little subsections x1, x2, x3, etc., and corresponding y values. And if we wanted to measure this arc, all we would need to do is figure out this distance and then add the next little distance, and then of course, with calculus, we could just make these distances shorter and shorter and shorter and add them all up. And that's essentially what we're going to do to find this arc length. And so what we can do with this case is think about, well, we're really looking for the difference of the x values being squared and the difference of the y values being squared. And with a little bit of algebraic manipulation, I can get this equivalent expression, which is the derivative, the delta, the difference of the x plus the derivative of the y, delta of the y over delta x squared times a delta x. And then these are the little lengths of each of these. This distance formula is equivalent to the length of each of these little subinterval lengths. And then basically I just want to add them up. So the total length would be add up all of these lengths. There's from I equals 1 to n of them. And a little bit of manipulation of this dividing would give me the square root of 1 plus delta y over delta x. This is the slope, and I'm going to square that, and then all of that's going to get multiplied by delta x. And so I'm doing the limit as n goes from I equals 1 to n of that. And of course, since this piece here is the slope, another way that we can calculate this, and we could come up with basically a formula S for arc length. This is equivalent to take the integral from a to b of 1 plus, and the way that we find the slope is the derivative of the function that we have evaluated at x, and we have to square it, and dx. And so this is where the arc length formula comes from. And this works, again, as long as we can take the antiderivative, which is as long as f of x is continuous on the AB interval. Okay, so let's take a look at an example of how to calculate an arc length using this formula. So in this example, we have a picture that starts at 0, 0, goes to pi over 4, and I want to know this arc length. And the function in this case is going to be ln of secant of x. So something quite complicated, and again, it's on the interval 0 to pi over 4. So, of course, this should be an x. The derivative of this is 1 over secant x times the derivative of secant x, which is secant x tan x. And these cancel, which is kind of nice. So the derivative in this case is just tan x. And since tan x is continuous on our interval, 0, 4, then we can use the arc length formula. So arc length, we're going to go from 0 to pi over 4. We're going to have 1 plus tan x in here. Tan x gets squared, and the derivative with respect to x. So this is the same as the integral from 0 to pi over 4 of the square root of secant squared x dx, which is the same as 0 to pi over 4 of secant x dx. And this integral has a form that's ln absolute value secant x plus tan x. And all of that is evaluated between 0 and pi over 4, which leads to a value of ln root 2 plus 1 when you do the substitutions. And we have the exact length of the curve shown in this picture, or the curve on this function between 0 and pi over 4. We can use a somewhat similar approach to find surface area of figures that are revolutions. So if you imagine having some sort of a function and it gets revolved around an axis, say the x-axis, then you start to create this volume of revolution. And if you inspect just one piece of this, just maybe this chunk at the end, this is a truncated cone. And so similar to what we did with arc length, we can actually find the surface of this by taking these circumference, these really small circumferences, and then measuring the arc length and using both the arc length and the circumference to estimate, make very small arc length changes to estimate and then calculate using integrals the surface area. And the formula looks like this. So the 2 pi is factored out from essentially the circumference 2 pi r. The radius is the height of the function. So this piece is from the circumference. And then we have to multiply that circumference by a small arc length. And so we have an arc length formula that looks like f prime of x. This whole thing needs to get squared dx. And so as long, again, as f prime of x exists and f of x is continuous on the interval ab, we can actually go and calculate this. And so let's verify one that you have seen before, I hope, which is, let's verify the surface area of a sphere of radius r. So we need to start with the function, and so our function is going to be a circle of radius r, so r squared minus x squared. The derivative of this function is negative x over r squared minus x squared. And 1 plus f prime of x, all being squared, to work on this piece in the middle, is the same as 1 plus negative x over root r squared plus x squared, minus x squared, all squared. And so I get 1 plus x squared over r squared minus x squared. And if I make a common denominator and then bring together the terms on the numerator, I end up with r squared over r squared minus x squared. So now I can set up this formula, s equals 2 pi, integral from a to b, but now I'm going from negative r to r. And then I have my original function, which is r squared minus x squared. And I have this new function that I've just created, r squared over r squared minus x squared, and dx. And this is square rooted, of course, because I have a square root in this formula. And you'll notice that this piece and this piece cancel out quite nicely, which leaves me with 2 pi integral from negative r to r of r squared dx. And of course, for those of you who are astute, I forgot to square root the top part of this. So this is actually just r here. And if I evaluate this, create a little bit more room, I get 2 pi r, and then x evaluated at r and negative r, which gives me 2 pi r, and then r minus negative r, which gives me 4 pi r squared, which some of you will know is the surface area of a sphere. And now we have a proof of where that formula comes from.